Hi, Adam is here. This is the second part of the 77th episode, The Competitive Developer with Thomas Wöttinger. And this time we are focusing on the GraalVM. So thanks, and now enjoy the show.
So my bachelor thesis was then on the real stuff, and I was super excited about that. We had, this conference call with people from America, from the Java team.
Cool.
Tom Rodriguez and is one guy there who was working on C2.
Okay.
And
so bachelor thesis. What about
HotSpot world.
Bachelor? So it means this was the assignment, the practical assignment during the university. So you had your work, and you were allowed to work on hotspot, so the real hotspot.
Yes.
So the question is,
yes.
how that? Because Sun had the research lab in Linz. This is the relation, right?
Correct. Yes. Because Sun had a long-term research collaboration with Linz since 2000, and it's still ongoing now with Oracle as well.
Yeah.
So this research collaboration is for 20 years now, and I was the fifth student or so in that collaboration.
Cool.
And I was allowed to do a project here with Hotspot. And what I did was a rebounds check elimination for the Hotspot client compiler.
But this was your lucky accident, right? So you studied at the university, who was also very into compilers, right?
Absolutely, that was a super lucky accident, and also that this professor was allowing me to do this type of project there.
Extremely cool. And the Hotspot was written in C++, I guess, right?
Yes.
And you enjoyed the assignment,
yes.
Or you cursed all the time about the quality of the hotspot code?
No. I did. I enjoyed the assignment because back then I couldn't. For me everything was here like godlike. Like basically this is just this. I didn't question any of the code quality because for me everything that I was seeing was must have been the best ever.
Yeah.
And it was a good. I mean, it has a good code quality. It was certainly. It uses a couple of C++ tricks that you need to get used to.
Mm-hmm.
But other than that, it was cool. And the client compiler is written in a very nice style.
Mm-hmm.
So I could do this rebounds check elimination. When I was finishing this assignment,
what does it mean?
Thinking,
your bound check and elimination. It means what does it mean? So if you done that, so what is the added value, right?
So the added value is that so Java will in the client compiler just run faster, because when you access an array, it was trying to remove the check on the index. That the index is within bounds of the array, and if the check is removed, then the program will go faster, right? And so I could achieve then on a benchmark suite like SpecJVM 2008 probably on average like I think even 10% or something.
Wow,
which is quite okay. And so I finished that patch, and after I finished it, I was submitting it to the hotspot mailing lists and everything, and I thought, okay, now the patch will be integrated. But unfortunately, it took quite some time until it was integrated finally. So it was only but it is now integrated. So these pieces of code are in the hotspot source base.
Okay,
but it took quite some time from the time when I was finishing it until it was integrated.
So I think this is the your bachelor work as a student. So I think this was the most impactful student work ever, I would say. Because if you think about this, so your work now runs on all JVMs, right? Worldwide. So they're like millions of projects.
That is true. But yes, that is true. But it only runs in the client compiler.
Yeah.
And the client compiler is, it is. Well, actually, it's still used as a tier 1 compiler. Yeah.
Yeah,
it was certainly very impactful in terms of because it's in the whole Java universe.
What was for you Java something special? Like you say, okay, this is really the hot stuff right now, or you just you optimized the hotspot compiler because it was just interesting task?
I think I was optimizing the hotspot compiler because the university collaboration was with Sun Microsystems. If the university collaboration would have been with Microsoft, I would be working on the .NET compiler.
I got you. And so what you did afterwards? So you optimized the compiler. So you were.
So after that, I was for my master thesis, I got the new assignment, and the new assignment was a graph visualization for the server compiler, for the C2 compiler.
Okay.
And I really loved that project because it's like basically taking the compiler graph of C2 and like displaying it in a very nice way. And I kind of like these visualizations and graphs. So it kind of combined everything that I like about it. And this was called the Ideal Graph Visualizer. So this was a graph visualization tool for the HotSpot server compiler. But as a side effect, now I could learn also the intermediate representation of the server compiler very well. So after these two projects, I had a very deep knowledge of both client compiler and the server compiler.
And you like that? So you like know the ideas in HotSpot, or?
Yeah, I mean, there's a lot of great ideas in there, and many of the great ideas from there we were then later using when we were doing the GraalVM compiler.
Okay.
Where we try to in the GraalVM compiler combine the best of both worlds.
Cool.
The best of C1 with the best of C2.
And the graph visualization tool is still available, or how it was programmed? In which Qt?
Yes.
Or what was it?
It was in Java.
Okay.
Java based on the NetBeans platform, and it uses the NetBeans visual library.
Cool. And you could still use it, run it, or get it, or
yes,
is it?
And you can still run it today. And because we later adapted this tool to be the graph visualizer for the GraalVM compiler.
Okay.
And it's still available, and I'm still using it, or the team is using it on a daily basis when we are debugging problems in the compiler. And this graph visualization tool is I think it's absolutely fundamental in terms of without that, I don't think you could build such a complex compiler, or at least it would be much more difficult because like finding problems in the compiler graph is just too hard without such a visualization tool. Because our compiler graphs often can have like, even 10,000, maybe even 100,000 different compiler nodes. And then it's just impossible to just print out some numbers on a console. You really want to have a graph that you can traverse.
Okay.
And so, yeah, this tool is still active in development. You can download it today from the Oracle Technology Network as well.
Just drop me a link and I will put it to show notes, so it could be interesting.
Sure, absolutely.
Very good. So what was then your next stuff? So you did the visualization tool, and then, you understood the hotspot. So what was your thinking back then? So okay, what's the next step?
Yeah, so then I was looking for a PhD topic, right? And at the same time, I got lucky because there was the Maxine project at Sun Microsystem, which was the Maxine Research VM. And the Maxine people, they were looking for interns in California. And they were approaching Professor Messenberg and asked, like, don't you have a student to send us as an intern? And I was very lucky to be then accepted for this internship in California on the Maxine Research VM.
Okay, the Maxine Research VM. Was it related to the project called Project Maxwell at Sun Microsystems?
I think Project Maxwell was a different one.
Because Maxwell was the idea. I found that back then, and I had the references to Sun Labs, but they disappeared. And the Maxwell was the attempt to create Java, the Java virtual machine in Java itself from scratch.
Oh yes, then it is exactly that one. Yes, I see that. Yes, it is exactly that project. Yes.
Okay, so Maxwell and Maxine were the same project.
Yes, I think they just renamed it to Maxine later on. I just see here a Project Maxwell paper from Bernd Matiske, Doug Simon, and Dave Unger. Yes.
Okay, perfect.
And yes, and Bernd Matiske was the lead of the Maxine project back then, and Doug Simon was one of the researchers on the project. And Doug Simon is now also still on the GraalVM team. He's leading the compiler efforts.
Okay, cool. Well, perfect. So you and the project was already started, or you started the Maxine project with so how advanced was it?
So the project was already very much advanced. So the project was it could already run a lot of Java workloads. And I was tasked with a small part of the project.
Okay.
Related to the debug interface.
Okay.
Where I was implementing the debug interface for the Maxine virtual machine. But for me, this was very exciting because it was like first time Silicon Valley, and I was just really hyped to go there and to prove myself in that environment.
What was your very first impression of California? So you arrived there, and so you have, you had some, you imagined something in Austria, how it will feel like, the Californian feeling. Then you arrived there. So what was your first impression the first 2 days?
So I was like, my impression was like lots of cars.
Yeah.
And because like everything's very big in Austria, you like much smaller. I would always walk to my work, for example, right? In California, you always need the rental car.
Yeah.
But then also, I mean, weather-wise, of course, always sunny, which is very different as well. And I think these were the two main impressions for me.
Okay. And where was it? Was it in the Sun Labs, right? In the
it was in Menlo, in Menlo Park.
Yeah, there's right now Facebook, I think, right?
Yeah, this is now the Facebook office. Yes.
Yeah, Menlo Park. Yeah, nice.
Yeah, back then it was still a nice office with small offices and stuff like that.
Mm-hmm.
I was recently visiting it also at Facebook, and they moved everything into open office space.
Okay.
And basically ripped out all the walls.
Oh, okay.
So back then, I think it was much more pleasant because we had small offices and could like better concentrate on our work there. And
you liked the team from the beginning, so it was like a nice environment to work?
Mm-hmm. Yeah, it was a nice environment to work. We also had like 7 different interns from all over the world.
Hey, cool.
And so it was fun as well. And we did, typical Yosemite hikes, etc.
Hey, cool. And what was the motivation for Sun to start the Maxine? As I remember, James Gosling mentioned it once that they need to do it because to make it simpler, and that Java could optimize Java. And the idea is at one point could be run faster than the static C or C++. This is my understanding of Maxwell or Maxine. Was it correct, or what was the main motivation back then?
Yeah, that was the main motivation, really, to just prove that Java can be used as a system language piece, and that this meta-circular optimization of itself will lead to higher productivity, right? Mm-hmm. So you will be more productive when you create the virtual machine, etc. Right? Mm-hmm. And and that was back then the motivation for Maxine. Mm-hmm. And the GraalVM project you can think of as the successor of the Maxine project, or as the project that finally makes the Maxine vision a reality.
And what is the relation between Maxine and Graal? Was it like, succession, or was it like a heartbreak and, starting over? Is it like, is GraalVM Maxine actually?
You can think of it this way.
Mm-hmm.
So what happened was that, I did a second internship the next year afterwards. Mm-hmm. And in that second internship, we were replacing the Maxine compiler mm-hmm. that was written from scratch mm-hmm. with a new version of a compiler that we called C1X, because it was the client compiler mm-hmm. from HotSpot. Mm-hmm. And we transliterated it from C++ to Java.
Mm-hmm. And were your bound checks optimization included? Was in this compiler, or was not included?
They were not yet included.
Oh,
it was
okay.
not yet integrated in HotSpot, unfortunately.
Okay.
but yeah, because it took a couple of years until they put it in production.
Okay.
But it was basically, and I did that work of doing this translation, this source to source translation, mm-hmm. which means I was literally like going, and it was a manual process, so I was literally going over every single source line of the client compiler.
Okay. This is now called transpilation, right? This is what the cool kids are doing with JavaScript, right. Like they transpile, how it's called, yes. TypeScript to JavaScript. So you did it, with C to Java, right?
Yes. There was a transpilation from C to Java. That's right. Yes. Right.
Okay.
And then later on, when I was then joining Oracle Labs after my PhD, I was joining Oracle Labs full time. Mm-hmm. I was joining the Maxine project, right? So when I was starting, I was joining the Maxine project.
Okay.
And but then we changed the direction of the Maxine project, because we found that doing everything in Java is might be too ambitious as a first step. Mm-hmm. So why don't we just focus on the compiler being in Java and hook this Java compiler written in Java back into HotSpot. And in this way, we can profit from all of the great runtime system of HotSpot, and we only need to worry about the compiler part. And when we did that, we took this C1X, this client compiler written in Java, and we hooked it back into HotSpot. And at this stage,
but this is not the javac compiler. This is the compiler which compiles the bytecode to the intermediate language, right?
Correct. Yes, this is the JIT compiler that is compiling the bytecode to machine code, not javac. That's correct. Yes.
Yeah, but the javac compiler, it was always in Java, right?
That is correct. Yes.
Okay.
Yes, correct. Yes.
Cool.
Yes. But here we're talking about the just-in-time compiler, which is the system software piece that is really generating the machine code in the end.
But why you get something out of it?
Right?
So if the JIT compiler is written in Java and the hotspot optimizes the stuff, I mean the most advanced or the most performance boost you would get from the hotspot, not from the JIT, right?
So you get a better performance if the JIT is producing better machine code.
Oh, okay.
So the quality of the machine code the JIT produces is typically the main determinant of performance.
Oh, okay. So I would
not everything. There are some parts of performance like garbage collector or sometimes the runtime system performance is also relevant. But the first level of performance is coming from the code quality of the JIT, meaning how good is the machine code that the JIT produces for your Java code. Garbage
in, garbage out. So if the JIT produces poor code, the hotspot cannot optimize it a lot, right? This is the idea.
Well, hotspot doesn't optimize the code anymore. It just installs it in the code cache.
Okay.
So if the JIT produces machine code, hotspot will just execute whatever the machine code says, right?
Okay.
So hotspot is it's starting to interpret the methods, right? And when a method gets hot, so a method becomes important, then that method is sent to the JIT compiler. And the JIT compiler gives back the machine code, and then hotspot installs that machine code, and then instead of calling the method in the interpreter, hotspot will just jump to that piece of machine code.
What I thought is that the JIT, produces the code and puts it over to hotspot. And hotspot looks at the hot methods and then optimizes by itself. But the hotspot is more like
no.
It delegates back to the JIT. So you are right. Then the hotspot really does not matter a lot, right? In this particular case, it's
Yes.
Okay.
Yes, it only matters when sometimes this machine code needs to jump to the runtime system because there's a complex operation or there is a lock, for example, locking. And in these situations, the runtime system's performance can also matter. But the main level of performance comes from the JIT mode.
Okay, cool.
From the JIT code and from the quality of the JIT. And so this was and here this C1X that you put into hotspot, we also replaced the front-end intermediate representation with a new intermediate representation. And this is then what we call the Graal compiler.
So the Graal compiler is like the what you port. So actually, you are one of the fathers of Graal, right? Because you actually ported or transpiled the C code to Java, and then it runs and passes to hotspot, and then there is a new intermediate representation. So right, so you're one of the fathers of Graal. You could tell us.
Yes. So I'm one of you can say the father of Graal is C1.
Okay.
It's the C1 compiler.
Okay.
Because the original code comes from the C1 compiler that I was translating from C++ to Java, and then we only replace the front end. The back end, in terms of the register allocator, for example, or the low level intermediate representation, is actually still the same as C1. So there's large parts of Graal, of the Graal compiler, that is the same as the C1 compiler.
And the intermediate representation, you say you adjusted the intermediate representation. What means you had also to adjust the hotspot or not?
No, we did not adjust hotspot at all. So the intermediate representation is the first. So we adjusted the front end of the compiler, meaning the intermediate representation that is created from the Java bytecodes.
Okay.
So the Java bytecodes are parsed into this first level of intermediate representation, and then we do the high level optimizations, and then we transform this into the low level intermediate representation. We do low level optimizations, and then we do register allocation, and then we create the machine code, and then only the final machine code plus some metadata is passed to hotspot.
Okay. So
and this compiler, among one of the interesting things about the compiler is that we put it back into hotspot, but we still also have it work in Maxine. And the Maxine project is a research project. It's, by the way, continuing. There's like a university in Manchester that is working on that. So there is this nice interface between the compiler and the runtime, which is called JVM CI, JVM compiler interface. And this enables the compiler to be used in hotspot, but then also in the Maxine virtual machine.
Okay, nice. And so you work on GraalVM project, and so you achieved the pure Java, let's say, compilation. And at one point of time, I think you recognize it could be more than just this, right? Or was it clear from the beginning that Graal could become the polyglot environment?
Yeah, no, that wasn't clear from the beginning. The beginning was just a mission to just do the Java compilation, Java cheat compilation. But then I always had the ambition to also execute JavaScript. And partly that is because JavaScript was my first language. So I like JavaScript.
So you wanted to have the gaming script experience in Graal, right?
Exactly. That's right.
Okay.
Yes. And another reason for that is that right between my university and joining Oracle, I was working for Google on the V8 project. I was working on the Chrome browser's JavaScript engine. Back then it was called Crankshaft Compiler, which was the compiler that I was together with a few people from the V8 team creating. And
how big was the team at Google back then for the compiler?
At Google, we were creating this compiler with 4 people.
Okay.
So I was one of them, and we were 4 people in total to create this Crankshaft compiler. And we did it relatively fast, and I was actually amazed by how fast they would then put it into the Chrome browser. And but so I had this experience with developing this JavaScript compiler, JavaScript cheat compiler at Google. So now I when I was doing the Java cheat compiler, etc., I was like, well, there seem to be so many components here that are the same. Between the Java cheat compiler and the JavaScript cheat compiler. Why can't we create one cheat compiler that can run both languages? Because it seems a total waste of effort to create a new cheat compiler for every new language.
Yes.
And so that was the motivation behind it. And so I was then like trying to get budget for this idea, but we actually didn't get much budget for it because management back then wasn't like they were not. They were like, oh yeah, let's finish this Java thing first, and then we can talk about other stuff. But it wasn't easy to create excitement on it.
Yeah, and they had already Maxwell, right? That's also the problem. There was Maxwell in place, so it's okay. We already have JavaScript, so what you're talking about, probably, right?
Exactly, and kind of what's the business case? Etc.,
yeah, exactly.
Right? And so we didn't have a lot of resources for that, but. So that was actually how we were forced to find a solution that would be able to do with very little effort. And originally we were thinking, okay, let's just take the JavaScript and then we convert that into GraalIR, and then we create machine code from this and put it to hotspot, right?
And GraalIR is Graal intermediate representation, right? So what are you talking about?
Yes,
okay.
Correct. Okay. GraalIR is Graal intermediate representation, and it's the representation we basically get out of the Java bytecodes. And this was the original thinking, and we even started these experiments, etc., to do that. But the problem was that this turned out to be quite complex, and the JavaScript is not a real match for the GraalIR directly, because JavaScript is very dynamic, and the GraalIR is like designed for Java bytecodes, which is typed, so it has fixed types, etc. And so this kind of failed in the sense that we figured out this is too complex, it's not going to work. So instead of doing that, we then came up with this idea. Inspired by the PyPy project. So the PyPy project is the project that does this trace compilation for Python. And it does so by doing sort of a partial evaluation of that Python code. And we now thought that we can use this partial evaluation also in the context of executing here like here to automatically create the machine code from a JavaScript interpreter that is written in Java. So instead of directly converting the JavaScript to the GraalIR, we are instead writing a JavaScript interpreter in Java. Our compiler already knows how to process Java bytecodes.
Say it again. This was the last 5 seconds you lost. So to write Java a Java interpreter for JavaScript.
Yes. So there was to write a Java to write a JavaScript interpreter in JavaScript. Sorry. The idea was to write a JavaScript interpreter in Java, and now the definition for this interpreter is Java bytecodes, and we already know how to translate these Java bytecodes to the GraalIR because this is the main thing we're doing all the time. So we can just do a special type of compilation for hot JavaScript methods where we are creating a special type of compilation under the assumption that the interpreter would execute just this one method.
The interpreter would execute just one method.
Just this one specific JavaScript method.
Okay.
So we would like the interpreter itself is written in a way that it can execute any JavaScript method, right? So the interpreter has like a root method that says execute, and it has a parameter, which is the JavaScript method it's currently executing, right? And typically when you would create machine code for that, you would just create machine code for this execute method, and the JavaScript method that comes in is just a parameter to that method, right? And what we do here special now is that if we see that this interpreter is called very often with the same JavaScript method. So the same JavaScript method is called over and over again. Then we create a compilation of this execute method of this JavaScript interpreter that is specialized for this JavaScript method that is executed so often. Yeah.
But in one point of time, you invoke the method with different types. You have to reject the compilation to do it again, right?
Yes. But so in this setup, we are basically treating the JavaScript method that is coming into as a parameter to this Java method. We are treating as a constant instead of a parameter.
But something similar, this is what Nasson also did, right? So they looked at how the JavaScript was executed, and if they assumed that there is a specific, parameters which have types, and then just optimize for that. And if the program was invoked differently, they rejected and did it again, right?
Right. No, but that's not what I mean here.
Okay.
So it's not about the types of the program.
Okay.
It's really about the way Nasson works, right, is that it would generate Java bytecode for each JavaScript method.
Yes.
So it takes a JavaScript method and then creates Java bytecode from that, and then it executes the Java bytecode that is newly generated. So with GraalVM JavaScript, we never generate Java bytecode dynamically. So the JavaScript methods are always only interpreted. So there's only one Java bytecode definition of the JavaScript interpreter. But there is never, like, if I load a new JavaScript method, I do not generate new bytecode. I will just also interpret this JavaScript method in the same interpreter.
So just to summarize, so what you did in GraalVM is the following. So just you wrote a JavaScript interpreter in Java and then compiled the interpreter, and what you got is the GraalIR, which is treated the same as a Java code. And what I'm thinking right now is actually genius, because you could use Graal to optimize the interpreter, which interprets the JavaScript altogether, right? So you could actually use that to self-optimize whatever is executed there, right?
Yes, correct. Yes, that is accurate. Yes.
Yeah, and then what you're talking now is just like a specific case. What if you get a specific method of the interpreter, and you pass to this method the JavaScript method, And then you have if it happens, a lot, then this is the hot method, and then you can optimize, right?
Yes, correct. Yes.
Yeah, cool. Okay, this is actually genius. This is like the NAS one was very simplistic, but I mean, for me it was also somehow similar, but bottom up. And in your case, you say, okay, we have the all optimization engine. So what we can do is actually to interpret JavaScript all the time and use our own GraalVM technology to optimize, right?
Yes. So we would use the existing GraalVM compiler technology to optimize. Yes.
Yes.
And in this way, we would avoid this code generation step, right?
Yeah.
I mean, I wouldn't say that the NAS1 approach was simplistic. The NAS1 approach would be the traditional approach, how you would execute the language on the JVM, where you translate that language into Java bytecodes. And we avoid that step by doing this multiplexing into multiple methods, not at the Java bytecode level, but when we optimize the JavaScript interpreter that is written in Java bytecode. And this has various advantages because the problem with generating the bytecodes is that it is putting a stress on the metadata of the JVM. And also the bytecode that is generated first is first cold, so it is interpreted, so it's not very fast. And so we the approach we take here is actually less intrusive to the hotspot runtime system. To the hotspot runtime system, everything looks pretty natural. The only thing that looks strange to the hotspot runtime system maybe is that for this interpreter entry function, so for the entry function of the interpreter, we might install a lot of different versions of the machine code. Because we install the generic version of the machine code for the interpreter entry function, and then we install specialized versions of the machine code for each hot JavaScript method. But for this entry method of the interpreter function. But it still uses only the Java bytecode of the interpreter as the definition of the semantics.
So what the question, what I understood is, so first you are just calling, your own interpreter, and then you find out, so the interpreter is for me like a command pattern, what I understood. So you're calling, you're passing the JavaScript function and it is executed. In one point of time, if you call it a lot with the same parameter, so you somehow freeze the entire interpreter as a specialized function, and then you have one generic interpreter, and then you have one like frozen interpreters for specific functions. This is how it works?
Yes, correct. Yes, absolutely. That's how it works. Correct. Yes. And in this frozen interpreter, we can now, when we create that compilation, right, we can now treat this parameter that's coming in not as a parameter, but as a constant.
Exactly. Yeah, that's
actually. And this makes us much better to optimize the whole interpreter for this specific function.
What I'm asking myself, so you started Maxine, to optimize itself. So for me right now, it should really be more like almost machine learning or magic, because you had the JVM optimizes itself. So inside the JVM, you have your interpreter, which is optimized by the self-optimizing JVM. So you could, in one point of time, I would expect, that you become surprised how well something gets optimized without any additional, doing, right?
Well, sure. That would be the best case. I mean, generally for us nowadays is that the more we put optimizations in GraalVM, the faster also the GraalVM compiler goes, right? So because it is compiling itself.
Okay.
But that meta circularity in GraalVM actually comes from another thing, which is the native image.
One question back to the interpreter. How you achieve that your JavaScript interpreter is so compatible with the recent ES6? So it's just like how you did it? Oh, no, not ECMAScript versions. Not ES6 is old. ECMAScript versions is what I meant. Yeah. ES6 is old, so the recent one.
Right. Yeah. So we have a small but very, very effective team on JavaScript, and so the nice thing for us is because we only need the interpreter. So there's only a single point of definition for all of the semantics. It's much easier to add new features to it compared to adding such a feature to V8 or to NAS Horn. It's much easier because you only need to change the interpreter. And writing an EST interpreter is the most natural way to execute a language. So this is why for us it is easier to keep up with some of these latest features, because the largest part of the runtime system, like the Graal compiler or anything associated with it, needs 0 changes, even if I change a lot in my JavaScript.
So, no, a funny story. A couple of years ago, so I don't know when it was, when GraalVM came first out, and on the GitHub there was not even an image for Mac. This was this time. So I installed the Graal and forgot about that. And what happened is my old NPM and Node builds run on Graal for 1 year, and it was very compatible, so there were no issues at all. But in one point, I upgraded something, and I look at that, and I did like Node version, whatever, and then found Graal. It's like, Graal? And then it without any knowing, I run, all my JavaScript stuff directly on Graal. So, and this was a big moment to say this is actually crazy. So I was able to use all the JavaScript features on Graal without any compatibility issues, right? So this is why I'm asking you right now, because this is very, very compatible with JavaScript.
Yeah. I mean, we are 100% compatible with the standard. We are executing the standard test 262, but we also are testing every week more than 100,000 Node.js modules.
Wow!
So every week we are running the tests on those and make sure that we get the same results as the standard Node.js.
What is the performance? Is it comparable to standard Node.js?
So we still have issues with the startup performance. So the startup performance is certainly substantially worse, unfortunately, at the moment. But we are working on mitigating that. In terms of the peak performance, it is comparable. Yeah.
Okay.
It depends. We have some applications that run a bit faster, some that run a bit slower. But the peak performance is certainly comparable. Over time, we think that we have a very server-style approach to our compiler. So in terms of peak performance, I think we will be able to be better in the future. And for the startup question, we are experimenting with ways to cache the machine code. So you might be able to do something like some snapshotting of the machine code in the future. So to also solve the startup problem, because on startup we are worse because we here this having a specialized VM helps V8 because they have a specialized compiler. They don't need to do this partial evaluation step, and the partial evaluation step is still adding some level of abstraction, therefore some additional time to the initial JIT compilation.
But what you could do in future, you could use JavaScript to communicate with Java and R, which is not that possible on Node. On V8, right?
Yes, correct. Yes. This is one of there's currently 2 main use cases where you would use our Node.js. One is this language interpretability. If you want to use JavaScript or Node, but you still have some Java library that you want to use, or if you have some R library that you want to use, that's one case where GraalVM shines. And the other one is where if you have a very large heap requirement, for example, and you want to run this JavaScript with the hotspot garbage collectors, then that are typically better on large heap settings, then this would be a second reason to run the Node.js on us. And we recently just had, for JavaScript itself, we had a blog article, I think today actually going out, that shows the performance for server-side React rendering. That is very good with GraalVM. So server-side React.js rendering is another potential use case here for GraalVM's JavaScript at the moment.
And this could be really interesting, because what you could do is you could have a server-side rendering, let's say, I guess you use Next something or React server-side. And then you could even, access from JavaScript Java code, to fetch some data from database and pre-render the stuff on the server, right?
Yes, exactly.
So this is why you get the whole enterprise integration for free, and modern front-end technology with backends, which you could reach out and call whatever you like. It's interesting. The R language, is it also similarly integrated like JavaScript? Like you have a Java interpreter for R, which is basically command.
Yes.
Okay, it's exactly the same approach for all languages, right?
Yes. Same approach for R, for Ruby, for Python, and also same approach for LLVM Bitcode.
Yeah.
And one of the things we're working on at the moment that we will publish soon as well is to use the same approach for executing Java.
Cool.
So a Java interpreter in Java.
So what it means is, so the Truffle, what it means is like a environment where you get access to all the commands, so you can call from one command to another command. This is how it works?
What do you mean by command? You can call from one language to another language.
Yeah, but how this works, you need something like an environment which has access to all the commands. I mean the the one interpreter in JavaScript, one interpreter interpreter is just a method representation in JavaScript. There's another method representation in R. So I need an environment where I can call the other interpreter. You know what I mean?
Yeah, I mean, so the way it works is that, well, one thing is from one language you can evaluate an expression of another language.
Yeah.
You can just call polyglot.eval.
Yes.
And then you type the language and then you type an expression.
Yeah.
And the other thing that works is we have you can export symbols into a global environment.
Yeah.
That works like a hash table, where you can export the symbol of a JavaScript method, for example, and then you can import it into your R program and then call it.
Yeah. But at this point of time, you have like the host language, like let's say Java, and I use I forgot the method, like Graal, I can execute JavaScript from there. So, and what will happen is like that the bytecode in one point of time will call the optimized frozen or not command, how we call it, the interpreter, and you get the results back. This is how it works. And if you have Java treated the same way, then, I mean, okay, this is not the issue because you always have to start in one language, and this language is ending being a bytecode in one point of time, and then you can call whatever interpreters you like. So there doesn't make any difference whether you're calling, R, JavaScript, Ruby, or whatever, right?
Correct. Yes. And this also means that we can even compile a method, like we can even inline between language boundaries. So you can inline a Ruby method into an R method or an R method into a Java method.
But then the method has to be frozen, right? So it cannot be this. It has to be the specialized version of the method, right?
Yes, that is correct. Yes, that needs to be the partial evaluated version of the method. Yes.
Okay, cool. So I understood a little bit about GraalVM. So this is why when we are doing a podcast, I think it is impossible to write it down, right? So I think it would be like 50 pages at least in the moment.
Yeah, I mean, we have a research paper on that. I think that's the best source for anybody who's interested. It's called Practical Partial Evaluation of Interpreters, and that has a very detailed description of the approach.
Yeah,
but
cool.
it's hard to communicate the approach very efficiently because it's just not the usual type of approach one would take. And so it's sometimes a bit hard to explain.
So this Truffle, this is the name. This is like the additional API which help us, to call the specialized version or the specialized versions of the methods, right? This is Truffle.
Yes.
Okay.
Yes, Truffle is the interpreter API. Yes. So all the languages are built on top of Truffle. And when you build a language on top of Truffle, you get these optimizations, etc. But you also get some language-independent tooling. So we also have debugging, profiling, and other language-independent tooling that's built in a way that every Truffle-based language benefits from it.
And because you know now what is actually used, so this is how it works. The Java interprets JavaScript. So at the end of the day, we know that actually 5 methods out of 50 are actually used, and others are just there but were never executed. So what you can do, so with static analysis, you can find out, what is actually used. I call it like tree shaking in JavaScript. This is like what they do all the time. They remove whatever is not needed. And then I think it's called SubstrateVM. So you can then say, okay, this is now the subset of all the stuff, what we're actually using. And then you can have provide, the native static machine code, which only contains what is actually used. This is how it works, roughly?
Yes, but so this native image
Yeah.
is done on the Java bytecode level. So and currently we do this ahead of time compilation only for the Java bytecode. We do not do it for JavaScript, let's say. So this is doing a static analysis. Yes, it is analyzing from the main method of your Java program. It is analyzing what is reachable, and then it is ahead of time compiling everything that's reachable into a final binary. And this final binary is very fast in startup and has like a low memory footprint.
Yeah, it's amazing.
Because
you can save 90% of the memory. And a startup, so I had some, we had some Quarkus project where we cross-compiled into native just for evaluations. And this is like, the startup time is like unreal, 20 milliseconds for simple projects and something like this.
Yeah. The startup time is like typically 50x better and memory footprint typically 5x better. The startup time is better because everything is pre-compiled and you don't have like class loading. You don't have an interpreter like interpreting your bytecodes first before they get JIT compiled. Everything is compiled and you immediately start with the compiled machine code like you would do with a C program. So this is why the startup is so much better. And the memory footprint is better because we don't need the metadata. So we do not need to load the names of the names of the methods and the bytecodes. And there's a lot of metadata in the GVM that is necessary to do this dynamic compilation, and we don't need any of that metadata. And specifically for microservices, that metadata can be quite substantial compared to the application data payload. And this is why we think that this is just native image is designed for here Java functions and Java microservices. And you can use several different microservice frameworks. There is Micronaut, there is Helidon, and there is Quarkus currently that are very well designed for native image. And we are also collaborating heavily with the Pivotal team on Spring Boot support, so such that Spring applications can also benefit from this native image compilation.
And what you mentioned already is the LLVM support. And what I ask myself, is it actually possible to use Java code and cross-compile it to WASM, for instance, WebAssembly? Have you any, research in this area, or is it completely out of scope of GraalVM?
We do have research in that area. We actually will have an upcoming intern project on this.
Okay.
And we had already a student at some point have something that would output, instead of a native image, would output JavaScript that would be loaded in the browser.
Exactly.
So we had that already, but we still had issues with the size of the JavaScript being a little bit too big, and we couldn't minify it appropriately. But I think with WebAssembly and maybe minified JavaScript, it would certainly be an option. Yeah, and with native image, currently you do have the option to create LLVM bitcode instead of machine code. So if you want to then later use LLVM, or you directly want to deploy that LLVM bitcode to iOS, you can do that. But in the future, I think one interesting thing to do here would be to output here JavaScript/WebAssembly, and then run the resulting image in the browser.
Yeah, I think the JavaFX guys are doing this, right? So they also use GraalVM to have a native image and ship it to Android, iOS, and desktops.
Yes, Jon Voss from the Kluon is doing a lot of work in this area, and he is they are using here GraalVM to deploy with the Kluon tools to Android and iOS.
Yeah, which is a really interesting approach, because then you can use one language, Java, and use to create applications to all platforms.
Yeah, exactly. You can here go to the mobile platforms, and it's suddenly it's very efficient there. It's actually more lightweight than, let's say, React.js.
Yeah.
Because you don't have an interpreter there. So from a performance perspective, it's really fast and lean.
I think the next big thing is actually the WebAssembly, because the WebAssembly not only runs on browsers, it already runs also on so CDNs and caches. For instance, there are companies which are shipping the workers, so-called workers, to caches, and they can run on a browser or on the edge. And with WebAssembly, you are running directly in browser very efficiently, and you could perform interesting tasks. So I think this could be a extremely interesting project right now, because we have Java high-level language, and this was very easy to cross-compile that to WebAssembly.
So WebAssembly, one of the issues we currently have on WebAssembly is that they don't have a good support for garbage collection. So they do have various proposals there to enable garbage collection in some form. But this will be the major missing piece for us to efficiently compile to WebAssembly. Because they are mainly designed for C, C++, Rust at the moment. So for non-garbage collected languages. And this is one of the major pieces, I think, in WebAssembly that would have to be added.
So the Graal output is also LLVM bitcode. So what are the other use cases to having LLVM supporting, as a beside iOS and the others? So do you have any interesting?
One use case here is to have the ability to faster port to other platforms. So LLVM has a lot of different platforms, weird platforms that you might not want to support directly with GraalVM.
Okay.
And then the LLVM backend can help there. And like we did some experiments whether we would get additional performance by running LLVM optimizations before we create the final image. But it turned out that the Graal compiler, the GraalVM compiler, is already good enough in terms of performance, and seems to, for this type of object-oriented code, provide already better performance than what would be achievable by an additional LLVM optimization phases.
Okay.
But other platforms is, I think, the main motivations.
What are the next big steps in GraalVM? So what do you have to do? So what's in the next iterations?
The next big thing.
Yeah.
There's a lot of smaller things that we need to catch up on. But we are like currently, we got a lot of good feedback from customers and users on GraalVM and from the community. We had a community workshop last November. Where we invited all of the major companies that have work related to GraalVM. So we had their participants from Red Hat, from Microsoft, from Amazon, from Pivotal. And I think it was a very, very energetic 2 days where we were discussing here the future directions for GraalVM. And so one of the things we're doing there in the community is to establish now a GraalVM advisory board where we will regularly meet with participants of these companies and discuss the roadmap, because we want to make sure that GraalVM becomes also that more vendors get involved in GraalVM, and we can coordinate our efforts there to make sure that it works nice with frameworks, etc. Right. So in terms of the main things for GraalVM, for GraalVM native image, the main goal for us is to further improve the compatibility, specifically to make sure that Spring Boot applications can be run on GraalVM native image without major issues. And this is a focus point and collaboration point we currently have with Pivotal. I think that's important. The history behind native image was that originally we thought we would use native image only to compile the Graal compiler itself. So because we just wanted ourselves to be not having to warm up on HotSpot.
Yeah, right.
And only later when we saw, people want to use this really for microservices, that we then had to do a lot of additional work to make it, to add support for more features, etc.
What is the native image? What is it technically? Is it like precompiled Java JVM, or what is it? So it's like 10 megs, or which are downloaded. If it's a you have to do GU native image, and it just installs itself. But what is it technically, this native image?
So when you do GU install, right, you just install the Java program that creates the native image. And the native image itself is just when it is a Java program that does first the static analysis with the help of the Graal compiler. So it is passing all the methods into GraalIR and does a static analysis of your whole application to figure out what has to end up in the image, and specifically figure out what from the JDK has to end up in the image. And once it has figured out the parts that need to end up there, it is invoking the Graal compiler on each of those methods and creating machine code for it. And then putting that machine code into a final binary. That binary contains your application machine code. It also includes a garbage collector that is written in Java as well, and also ahead of time compiled. So it does include a garbage collector, but it does not include other parts of a runtime system that you would typically find in a JVM, like class loading, metaspace, or a cheat compiler, for example, right?
Yeah.
So these things are not there. The only runtime component that's in native image really is a garbage collector. And it can also snapshot part of the application heap. So you can use native image to, for example, load a certain configuration objects and then snapshot them into the image, so they are immediately available when you start it.
And why I have to install this tool separately? So I have to download GraalVM first and then do the GU native image. So why there are two steps?
So this is just a packaging decision. Also has to do with the licensing.
Okay.
Where like we currently have different licensing on these components.
Okay.
Specifically, native image is still considered as a early adopter technology.
Okay. And if you compare the performance of the native image and compiled bytecode, so for, let's say, hot methods, how better is the JVM still comparing to the more static native image code? Do you have a rough idea so how faster the JVM interpreted code still is?
Yeah, so this depends on the type of code. I would say between 20% to 50% faster.
Okay.
Is on the peak throughput side of things. And there is a few reasons for that. Some are related to the way our runtime system is built. So, for example, on save points, we need to optimize them better. We currently do not use signal handlers for save points, and we should use signal handlers for better performance. Some is related to the garbage collector itself, where the garbage collector native image is currently very basic and does not provide the same amount of throughput. And the third reason is that some of the compiler optimizations on Graal are just better tailored towards cheat compilation. And we are working to resolve all of these three issues. We will very soon have a preview of a G1 based garbage collector in native image.
Okay.
And we are also working to remove the issues on the save point performance and the issues related to the optimizations that are missing for ahead of time compiled code. And our goal is to reach the same meaning like plus minus 10% maybe performance on the ahead of time compiled code compared to the cheat compiled code.
Yeah, so the JVM will always be faster a little bit, but the native code will be almost as fast as the Java, right?
Yeah, I do not think so. I really mean here plus minus 10%, means that sometimes the EOT code might be faster also on peak performance.
Oh.
There are situations where you can do better on the EOT side of things. because an example is, for example, instance objects on. If the JVM is lucky with the profiling, they can be really, really fast. But if you have an instance of interface that is very polymorphic, for example, the JVM will be in cheat mode relatively slow to perform that instance object. And in our ahead of time compile mode, because we know the set of classes, we can make every instance object in constant time. So there are some scenarios where having a hard boundary on the set of loaded classes can be better. And another thing that we're working on for the ahead of time compile mode is to do better compression of data structures, which might add additional performance. So I do think it will really be a plus minus 10%, meaning we will be able to show also better performance sometimes with the ahead of time compiled.
But with the native image, you will have to perform lots of optimizations up front without seeing the program actually running. So can this be ever faster than all the possibilities of JVM, where the JVM is able to observe, the method execution and apply execution specific optimizations? So in theory, could you reach the performance by AOT or can be AOT as fast or even faster than the JVM? I mean, from the theoretical perspective, it's impossible, right?
So it is true that you have a disadvantage here in terms of not having the profiling feedback information.
Yeah.
And the profiling feedback information is one part that feeds into the compiler. So now there's several points to that. One is you can also do profile guided optimization ahead of time. Okay. We do support that in GraalVM already now. So you can create an image and you will be able to create an instrumented image, and you run that instrumented image on example workloads and create a profile from that and feed that profile into a ahead of time compiled compilation.
Perfect. This is perfect. So, I mean, then you can be faster, because if you have the information, that is actually genius. So you can run your system like, in instrumented mode, then you have the profile information, use it for AOT, and then it should be faster. Yes.
Correct. Yes. And specifically the advantage here is that in this mode, you yourself are deciding how you train your application.
Yeah.
Meaning you can, for example, train your application on a corner case because you want to be very fast on that corner case. Whereas in the cheat mode, the cheat compiler will always optimize for how the application behaves during the startup, and which might not be always what you actually want. So there are scenarios where having this, having the cheat compiler actually pick up the wrong type of profiling. Whereas in this ahead of time compile mode, you can be more deterministic also. So you're less dependent on any startup uncertainties of your application. So that's one of the advantages there.
So you could even do a little bit machine learning, right? It sounds like machine learning almost. So you could do, you can just learn as you're going and then apply.
Yeah, I mean, one of the things that we're from a research perspective we're going into here is to maybe have like some of this automated on a Kubernetes infrastructure, where the gathering the profiles, etc., is like automated, and then you will not have to do this yourself. And then you create a native image from profile that was gathered from a previous deployment of that Kubernetes container.
Nice. What I wanted to know is just the stability. So right now, if you compare the stability of the interpreted or AOT code, are both exactly the same, or are there cases where the JVM could work and AOT would crash, let's say?
So from a stability point of view, it should be very similar. It's the same compiler that we are deploying there. We have the GraalVM compiler run in production at various companies, including Twitter, since years now. We also have it running in production in the Oracle Cloud infrastructure with millions and millions of machine hours. So we certainly for the compiler itself have a very high level of stability, and the AOT mode is maybe slightly less stable, slightly less tested, I would say, but it's still using the same compiler, the same mechanisms. So I don't think there would be much of a difference from a stability point of view.
Yeah, and in like microservice like infrastructures, you have something like Kubernetes with no liveness and readiness probe. So at any point of time, the pod can be restarted in the next 20 milliseconds, and you're ready to go, right? So there's not like a lots of risk in such.
Yeah, exactly.
Yeah, exactly. Just as
yes,
okay.
yes, and this native image is really something that is encouraging here a design of multi-process scaling. So you scale up your application with multiple processes or multiple containers, and each container will be very small and very fast in startup. And we think that this is an exciting new type of way to run Java, and we really believe that this is an enrichment to the Java ecosystem. And we're happy to see other companies like Red Hat, for example, with Quarkus, or Pivotal now with Spring to agree with us on that point and work together to make here native image and Java work really, really well for microservices.
I know, yeah. I can just give you also feedback from my project. So the GraalVM is a big thing, and and what is also important, marketing. You shouldn't underestimate that. So what I usually hear, Java is slow or consumes memory. And what I do the first is just, show with Quarkus, for instance, right now, the native compilation and how fast it starts and, how small it is. And then the whole discussion just stops because they see, so it is actually very, very fast and small. And then we can focus on the business stuff and not, talking whether Java is the appropriate language or not.
Yeah, absolutely. And here you can now show that with Java, you have a choice. You can do the native image stuff or the JIT stuff depending on your needs, and it's really a choice for you, and it makes the whole set of possible application of Java much larger.
Yeah, and are you aware of unikernels?
Yes, and we are actually, this is another direction we're going. Is instead of creating a native image, we are thinking of creating a unikernel that has your application baked in.
Okay, this is what I thought the first time. So it's like this would be actually even better that you can just have like go a step further and have the whole, let's say, operating system with your or a subset of operating system with the application, right?
Yeah, absolutely. We also think this is a very interesting direction, and we have explorations in that area. And because this is what we figured out, that after we got the startup down to this 20 milliseconds, we suddenly kind of the container startup is dominating now. So let's optimize the container startup.
Yeah.
And our goal here really is a platform where you can scale up and down in like maybe 50 milliseconds, like including your container, or maybe 100 milliseconds, including your container and your application. And this would enable very efficient usage of resources because you scale up and down so quickly.
Yeah, and you have no programming. Java programming language on top of it. Another question regarding the native image: is there any possibility to monitor that in production? Let's say, I don't know, is it JMX or something similar, so that you can just ask the native image how it's doing?
So currently, I don't think there is much of that, but we do have ourselves some work going on to enable some JFR-like monitoring, and I know that Red Hat has proposed to work on some monitoring as well. So there will certainly be monitoring in the future. I do not think that you will add sort of JDWP or these debugging protocols on top, but at least the monitoring will be available in some form.
Yeah, and actually you could also get the profiler information you get from the interpreted mode, not from the native. Okay, perfect. Yes, so and what are you hiring actually?
Sure. I mean, we are always hiring.
So, but then
we are hiring.
But then the students will have to beat you in the programming competition in order to be hired by the GraalVM team, right?
Of course, that would be even better.
Okay.
But yeah, we are not always. It's one possible skill. It's not a mandatory skill. It's not programming competition is not everything here. But we do hire both full-time and also interns. Where we have this year actually a lot of interns that we have in our locations. We have a very large amount of locations in Europe specifically, in Zurich, Linz, and Prague, and our main locations there, where also the main part of the team sits. Large parts of the former NetBeans team is also on GraalVM to help with tooling in Prague. and I'm very happy about that as well. So we have a very strong tooling team on the project, and we always welcome here people who want to join the mission. Or also people who just, as maybe they don't want to be hired, but they want to talk about GraalVM or help us in any other way, give us feedback on GraalVM. We are really very excited to work with the community and to get others to tell us a little bit what are interesting directions, what would be kind of good next step, because we are we are more like a research and core technology team, and we are not we don't have a lot of experience with in praxis in terms of like running enterprise Java applications on the team itself. So we are very grateful if people who are deploying such applications in praxis give us the right type of feedback so we can go in the right direction and focus the improvements on the right spots. And there's still, I think, many new innovations to come in GraalVM. It's really just the beginning at this stage, and I think there will be much more exciting things coming out of the project. Now that we have achieved the basic level and the first releases, there will be for sure some more exciting things coming out of that.
Yeah, cool. And so where people can find you on the internet, or do you have some links for us?
So GraalVM.org is the main website. This is where we also have a link to community, where we have a link to our Slack channel, where you can speak with the core team, or also you can chat with me directly. And we are on Twitter at GraalVM. I'm on Twitter at ThomasWUE, where I'm also happy. My DMs are open, direct messages are open for any inquiries. And so we are happy to get connected.
And now the last question, the really last question is, so all your speed up, you skipped one class in gymnasium, then you were very fast in study. So did it pay off? Now you really enjoy the time, or will you take vacations in one point of time, or what's the strategy right now?
So it absolutely paid off, and I mean, I'm not really taking vacation, but I'm enjoying my time here, working on GraalVM.
Okay.
And also actually,
so it is actually vacation, right? So comparing to learning about operating system and hardware, now you have the vacation, right?
Yeah, it is kind of like vacation, and specifically now I'm on this longer trip to GraalVM user groups and customers that I'm combining a little bit with vacation.
Cool.
So I was recently in Seoul, in Taiwan, in Tokyo, in Shanghai, in Singapore, and currently in Australia, where I will have my next user group meet up next week. So one can say I'm a little bit of a tour of Asia, talking about GraalVM, and I can also combine that with vacation. And it's certainly more exciting than sitting in some school or university course.
Yeah, perfect. So lessons learned means, if you can, skip all the classes and then you get vacation afterwards, right?
Sure, absolutely.
So thank you. Bye.
Bye, cool. Thank you, Adam.